Okay, welcome everyone. Our first speaker is Frederik Benirschke. He will talk about the boundary of linear subvarieties. Please.
Yeah, thank you very much for the opportunity to present a part of my thesis here in this colloquium style talk. So, yeah, I want to talk about the boundary of linear subvarieties, and somehow I'm going to spend most of my time kind of explaining what those linear subvarieties are and why we care about them, maybe, and just in the very end, maybe we'll tell you what my contribution to the subject is. So, but first, let me introduce the main object of what I study. So most of the time I consider, I think about abelian differentials. So what I mean by this is always a Riemann surface of a certain genus, so it's a logical surface, but I always have a complex structure, and then I equip it with a holomorphic one form. So it's just, and so locally it just looks like dz in a local part. And the reason I consider them as pairs is that usually I'm not so much interested in just a single abelian differential or holomorphic one form. What I really care about is the collection of all of those. And so the main player of my talk is the stratum. So the stratum is a moduli space of abelian differentials. And for people that are not so familiar with moduli spaces, don't think of them every day, this maybe is a little bit of a scary object. But I mean, so at the moment, I think of it just as a set, and as a set, it consists of all possible pairs where X is a Riemann surface and omega is a one form of it. And I would call this a stratum. And so really, this is of course more than a set. This is really is a nice manifold, and I'm very interested in what's the geometry of this space. Okay, but this is kind of this is a highbrow point of view. Like some moduli space is very abstract. So what I want to convince you now is that you can actually think of the space in a very concrete, down-to-earth way, and you can actually draw pictures to understand the space. So the thing that I'm going to spend a few minutes on, that there's a dictionary that you can take in the abelian differential, so the Riemann surface in one form, and you can realize this as a polygon in the plane with parallel sides. And I'm going to explain how that works in a second. But the upshot here is that you can think of this moduli space just as a space of polygons in the plane. And that's a very concrete object, right? I mean, everybody knows how to draw polygons in the plane that have pairwise parallel sides. So everybody knows really how to construct a lot of different abelian differentials. And this kind of, this dictionary is a very powerful tool in the field, because you can on the one side, on the space of abelian differentials, you can do algebraic geometry. On the other side, in space of polygons, you can really do very soft topological constructions, and the equivalence of the two gives a very powerful connection. Okay, so but now let me explain a little bit how this works. How do you go between abelian differential and polygons in the plane? And I think probably most of the people have seen similar constructions already, but I think I will still spend a few minutes. So we're going to start with some polygon in the plane, and I wanted to have pairwise parallel sides. And now I'm going to choose a pattern on how I identify parallel sides using a translation. So in this picture here, I've marked the sides that are going to be identified by the same Roman numeral. Right, so the way you understand this picture here, you have the 1 and the 1 that are supposed to be identified along a translation. And X is just the quotient space that you obtain from this procedure, where you just identify the sides. And so the nice thing about this construction is that, well, first you can think of this as polygon in the real plane, but I want to think of it as sitting inside the complex plane. And since I'm identifying translations, and translations are just holomorphic functions, this quotient is not just a topological surface, it naturally has a structure, a complex structure on it. It just inherits a complex structure from C. And because the transition functions, which are translated are holomorphic, the quotient inherits this complex structure. So I've naturally constructed a Riemann surface starting from a polygon. So how do I get the one form? Well, it's also very easy because on C, I just have the one form dz, right, where z is a natural coordinate in C. And the thing is, dz is invariant under translations. So the one form dz now descends to one form on the Riemann surface, and it will be holomorphic, and it might have zeros, and the zeros occur exactly at the vertices of the polygon. So this at least gives one direction of the construction. So starting from a polygon in the plane where you have parallel sides, you can always construct a holomorphic one form together with a differential. And now I guess what you have to believe here is that this is really gives you a one-to-one correspondence of objects. If you do the right, and then there's some certain equivalence relation that you have to take on both sides to make this actually a bijection. But for all I'm going to say is it's really okay to think of the space of holomorphic differentials as the same as the space of polygons in the plane. And hopefully the space of polygons, most can agree that this is a very concrete thing. And so why is this very useful, this equivalence? So there's two consequences that we get quite easily from this description. So the first consequence is that we get an action of the group SL to R on the space of abelian differentials. And I'm going to explain how this action works in a little bit and how how it acts on the polygons. But this action is really the main player in Teichmüller dynamics, and people have spent a lot of energy on trying to understand the dynamical properties of this action. And there's a second consequence that I will need that also comes from the description of polygons, that you get a natural coordinate system. So the space of abelian differentials becomes a manifold. It's not really a manifold, but for all intents and purposes, you think of this as a manifold, and we can describe the coordinate charts very nicely once we draw the polygon. So I'm going to explain how this will work also in a second. But for now, I just want to record that we get those two consequences from the description as polygons. Okay, so I now want to start describing this SL to R action a little bit, because I mean it's very important for what I'm doing. So the thing is now that SL to R just acts on C. If I think of C as R2, right? Then SL to R just acts on R2 by matrix multiplication. And since I have a polygon in R2, right, and now I can just take the image under this action, I get a different polygon. And the nice thing is that the matrix multiplication keeps parallel sides parallel. So what really happens is I take a polygon and I act on it by the matrix multiplication. Then I get another polygon where I still have parallel sides. And since we identified the stratum with the space of polygons with parallel sides identified, we really get an action on the stratum. So this is very abstracted, but we can draw pictures very easily of this. So the picture now looks like this. So for example, if we take an L-shaped surface on the left, I mean, I haven't drawn the identification, so you can choose any pattern of how you want to identify parallel sides. Now, how does this action work? For example, let's take the matrix 1, 1, 0, 1 and SL to R. Then, well, I just take the image of this polygon under this action. So this matrix in particular is just, here's my polygon in this way, and I get a different polygon. So I have parallel sides, so I get a different Riemann surface in a different one form on it. And then this is really how this action works. Okay, and I'm going to say something about the dynamical properties of this action in a little bit. But before I can do this, I need the second piece. I also need the period coordinates. So those are the natural coordinate systems. So how does it work now? So we take some point in the stratum. So we fix some base Riemann surface and the base differential, and then we represent this as a polygon. right? So for example, it could be like this. All right, so and here now instead of Roman numerals, the colors denote which sides are identified. So this now is a polygon that represents my base point. And how the coordinates work? Well, the coordinates work now work as follows. I'm going to consider, well, I don't know, I call it complex lengths of the polygon. Well, what I mean by this is just, well, take some side of the polygon, for example. Can people see my mouse movements?
Yes.
Okay, so let's take this red side on the right, for example. What I mean by the complex length is just, I mean, think of this as a complex vector, right? And so it has a real imaginary part, and this number, right? It just points from this vertex to this vertex, and this complex number. This is what I call the complex length. And now you can do this for every side of the polygon, and this collection of numbers now gives you a coordinate system. Right? And so how does it work? Well, the idea is now that you can take one of the sides and you can just wiggle it a little bit. I can move it a little bit to the side, and then I just have to move the parallel side accordingly. But I can do this, and I get a different polygon. And so the theorem here that is stated as a fact in quotes is that by basically just wiggling the sides of your polygon just a little bit, you can describe a whole neighborhood of the strata. So they give a nice coordinate system of the space of differentials. Maybe this is a good time to see if there are any questions. Okay, so I mean, I have explained now the two basic things that we have on the stratum, which is the SL2R action and this set of coordinates, which I call the period coordinates. So they call periods because those complex lengths, they're really just integrals of this one form dz along those line segments, right? So that's why they're called periods of the period coordinates. Okay, but now that I have those two objects, I can tell you some of what's the main big theorem in the field that has been quite fantastic, and it's pretty deep results. But they basically say that this action of SL2R that I have on the stratum is extremely nicely behaved. So, I mean, I'm summarizing several papers and theorems here. So I'm going to attribute this to Asker, Mulakani, Mohammadi, and to Philippe. But then there's subsequent papers just by Asker, Mulakani, and there's a bunch of other people that have contributed to this. I mean, this has been a major development. But so what does it say? It says, well, so we take a point in the stratum, now I have this action of SL2R, so I take the orbit under this action. So the orbit itself is not such a nice object, but just take the orbit closure in the natural topology that you have on the stratum. And for example, one way to define the topology is by saying that wiggling the side lengths of your polygon a little bit, this is a continuous deformation. So this determines the topology. So take the orbit closure of a point in the stratum, then those are always algebraic varieties. So they're very rigid objects, but they're even better if I now look in this those period coordinates, so this natural coordinate system that I have on the stratum. Then they're just given by linear equations. And the linear equations have only real coefficients. So in some sense, those varieties are as nice as possible. I mean, linear equations are as easy as it gets in some sense. So what this basically tells us that we, even if you're doing dynamics and you're just interested in the dynamical properties of this action, very soon you'll land in the realm of algebraic geometry, because now your orbit closures are algebraic varieties. Okay, so one of the caveats here is that orbit closures are never compact. So if you want to do algebraic geometry, or just in general, if you want to study those orbit closures, things become much nicer if you have compact objects rather than something non-compact. So one of the things that you would like to do is to somehow compactify those orbit closures in a nice way. and then this is part, I mean, and I do contribute a little bit to this problem. All right, so how does it work now? So I'm going to try a little bit to explain how we can take those orbital closures and trying to make them compact. So the idea is now that the orbital closures, they live in the stratum. So the stratum itself is not compact. So that's already an issue. But recently, there has been a construction of a very nice compactification of the space of differentials. So this theorem, due to Manfred Schenz and Grzeski and Möller, is that they construct a very nice compactification of the space of differentials. And this compactification has all the properties that one could basically hope for. So for once, it's a smooth manifold, and I mean the construction is very complicated, so I won't be able to say too much about this. But the boundary of this compactification has a very nice geometric description. So it consists of nodal Riemann surfaces. So nodal Riemann surfaces, just you take a collection of different Riemann surfaces of varying genera, and then they can touch at finitely many points. So the picture down here looks like this. And then additionally, on each of those Riemann surfaces, I have now a one form on them. That is also supposed to be holomorphic. It might have a few poles. But this is how points in the boundary look like. So they still look very similar to abelian differentials. The only difference really is that my one Riemann surface, maybe now it's split up into different disjoint Riemann surfaces. And the only thing that I will really need from this is that on the boundary, you still have an analog of a natural analog of those period coordinates that we had on the space of differentials. And the way this works is just that, well, you think of your nodal Riemann surfaces, right? I mean, it's just a bunch of different Riemann surfaces. So on each Riemann surface, you have differential, and this differential lives in a fixed stratum. So on this stratum, you take the period coordinates, and now you just take a product of all the different components that you have, and this way you get your coordinate system. And yeah, that's really all I need from this compactification. And now what I can do is, well, now I take my orbital closure, it lives inside the stratum, and the stratum we have now compactified by the space psi. So now what we can do is, well, we can't just compactify our orbital closures, but just simply taking the closure of those inside this compactification psi. Right, so you take the closure inside a compact space, so this is now compact. So this is a very naive way of compactifying these orbital closures. So what can we say about the structure of those, the closures of those orbital closures? Okay, and then so this is one of my results, is that you take an orbital closure for the SR direction that lives in the stratum, and then we look at the boundary of this orbital closure inside this compactification psi that I just described a little bit. And then this boundary now is again given by linear equation. So the orbital closure, right, by this theorem of Philippe and Zakani, Mohammadi, that locally in period coordinates, it's just given by real equation. And so the statement here is that the same is true for the boundary. It is still given by linear equation with real coefficients. So the general statement maybe is not so important, but the slogan is very easy. You take a linear subvariety, so something that is defined by linear equations among the periods, you take its boundary, and then it's linear again. Right, so somehow what happened is the boundary looks very similar to it. It has a very similar structure than the original one. It's still given by linear equations, but what happened is now that since it's the boundary of something, the dimension decreased by 1. So one of the motivations of why one would be interested in the boundary is that you can now do some kind of inductive procedure to study this orbital closure. You start with an orbital closure, you take its boundary, it's again given by linear equation, but now it has 1 dimension less. And then you can reiterate this procedure. You could take the boundary of this, it's again given by linear equation, but the dimension drops by 1 at every point. And if you can somehow classify those orbital closures or things given by linear equation in very, very small dimensions, the hope is that this helps then to also helps with the classification problem in arbitrary dimensions. Yeah, so that's maybe a good point for me to stop.
Thank you. Any questions, comments?
Can you think of this compactification in terms of polygons somehow, like degenerate polygons or something?
Yes. So you can. So what happens is that even if you start with a holomorphic one form in the boundary, your differentials, they might require poles. And if you have a differential with poles, then you cannot represent this anymore as a compact polygon, but there's still a way of representing this as some kind of infinite surface. So the easiest example is, for example, if you want to draw a picture, take on the sphere, you want a differential with one double pole, then you can draw the picture that you draw is just a copy of the plane C, right? Because then you take the differential dz on the plane, and this is somehow the polygon that represents this differential. And the double pole, you don't really see it because the double pole is hidden at infinity. But there is a way of drawing nice pictures for the surfaces with poles. They're just, I mean, they look degenerate. There's in some sense degenerate polygons, like the plane, for example.
I presume that poles are along the nodes and they have opposite residues. So I don't know, like how that looks like in a polygon.
Yeah, they don't. So if they have simple poles at the nodes, then they have opposite residues. But one feature of this compactification is that they might have higher order poles. So for simple poles, there's a picture. You can, like, a simple pole always looks like a cylinder, and the residue is just basically the height of the cylinder. And so what you can then, so what you will have some infinite copy of C, and inside you will see some cylinders sitting in there, and this will give you simple poles. But then there can be higher order poles, and the picture of those looks a little bit different because there's no matching residue anymore.
Can I ask a question?
Mm-hmm.
Have people thought about for higher dimensional varieties where tonality holds? You know, like abelian variety with one forms, or K3 surface with two forms, and asking similar questions?
Well, what kind of question are we exactly?
Period coordinates, but I don't know if there are good SL2R actions or things like that.
Yeah, but I don't think you already. I mean, already having the period coordinates are somehow the basics here, but I don't think you have necessarily an analog of period coordinates even in this case, because the duality theorems are not really about. I mean, this is somehow what's different. This is about a single one form or a single form. Well, duality is usually you take the whole basis of one forms, you take the periods of the whole basis. That this somehow recovers your variety. But what we're here doing, we're not taking a whole base, we just take a single one. So the situation is a little bit different. And I don't really know what can be done in this generality.
I have a question.
Yes.
So your pictures of the compactification look like the nodal surfaces look just like the pictures in the Deligne-Mumford compactification of surfaces themselves. Yes?
Yes.
So I'm asking, suppose you have a moving family of surfaces in the Deligne-Mumford situation that's going to the compactification, going to the ideal at infinity, and there is a holomorphic one form that follows this. Does this holomorphic one form actually converge to a holomorphic one form in the Deligne-Mumford compactification without assuming it's in the orbit of SL2R? Just it's a question about holomorphic one forms.
Well, I mean, if you have a family, then it does converge of differential. I mean, basically the answer is yes. I mean, if you take a family of differentials and then converges to some differential on the limit. So the thing is, this compactification actually is a little bit more refined in that, so what can happen if you do this is that in the limit, your differential could become identically zero on some components. And then you just somehow lose information on what happened on this piece. So this compactification that I'm talking about has some more information, because then, well, there's some rescaling procedure that you can do that along this family you rescale by do some kind of renormalization procedure that in the limit you'll actually get a non-zero differential on this piece that recovers information. So you actually have a little bit more information than just what is the limit. You also have the information at what rate, like how fast did something degenerate and converge to the boundary.
Okay, so you're saying there is a limiting holomorphic one form.
Well, it doesn't have to be.
Scale, if you rescale appropriately.
Right, yes. It doesn't have to be holomorphic though. So one of the things is that even if you start with holomorphic things in the limit, you might get poles at the nodes. But it's basically holomorphic.
So any chance that the slogan can be turned into a theorem that generalizes the theorem above? So any chance that that theorem holds in more general setting than just orbit closures?
Well,
like yeah, the boundary of linear subvarieties are linear subvarieties.
Yes, well, so what I really prove, the statement of what I prove, it doesn't really, it's not concerned with only orbit closure. So I study a little bit more general situation where you can be given by linear equations. They don't have to be over the real numbers. They can be complex equation among the periods. And this is what I really call a linear subvariety. It just needs to be given by linear equations. And yes, so then the same statement still holds. So from my point of view, the fact that orbit closures have real coefficients, they don't really play a role in what I'm doing. So if you have something that is given by arbitrary linear equations, complex coefficient, it's still true that the boundary is again given by linear equations. So it's part of what I prove.
Okay, then. Thank you.
One quick question. So how is the result depends on the compactification, or do you think this? Because I know there are lots of other compactifications.
Well, but I mean, there's not so many good compactifications. Well, so the thing is, this statement only makes sense if you have an analog of period coordinates on the boundary. So you need, so first of all, this implies that you need some compactification that is smooth, because otherwise, sometimes you can't make sense of coordinates. And I only know one compactification that is smooth and has this analog of period coordinates, and that's this compactification I mentioned. The other compactification that I know, they're either singular or they're smooth, but well, no, actually, the other ones I know are just all singular. So there's no hope of proving a similar statement.